Now, as I find with the 5 coordinates here as obtained from the table, I find that when I take all the x coordinates, then I clearly see that the lowest is -1 and the highest is the 5. So this is the lowest and this is the highest in the x coordinate. And when I take similarly in the y coordinates, I see that the lowest is 0 but the highest is 20. So this makes me understand that the y values which are taking on the y-axis must have a larger scale, a smaller scale where more values should fit in from 0 to 20. But an x-axis can have a suitably smaller scale with many values fitting in. So in this case, let me take the scaling initially starting with x and y-axis. This is x-axis and this is y-axis and this is origin and how I get this. To start with, I just take 1, 2, 3, 4, 5, 6, 7, 8, etc. Then in the negative side, I get -1, -2, -3, -4, -5, -6, -7, -8, so on and so forth. Then the scaling here, I take small scale because I need to fit in 20 values. So I take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20, or the values which are taken on y-axis. And of course, with this would be -1, -2, -3, -4, etc. Now let me start plotting each of the points as obtained here. -1 and 13 starts with -1 on the left and 13 on the y-axis. So this would be the point where the first coordinate lies. The next, for 2 it is 0. So when I start with 2, this would give me 0. Therefore, this is the point on x-axis, which gives me the second coordinate. Similarly, 3, 0 is also available here. So this would be the coordinate between 3 and 0. Now I have 5 and 6. Therefore, my x equal to 5 and y equal to 6 is somewhere here. Then similarly, I have for -2, this is 20, which comes somewhere here. So the values which I've taken has given me different points where, interestingly, it gives me the conclusion that when I just join the points, and also I have the y-intercept as 6, so this graph must pass through 6 and then like this, like this. This is similarly somewhat the shape of a U-shaped graph is what I obtain for a quadratic polynomial. Y equals x squared minus 5x plus 6 would be somewhat in the shape like this. So what are the learning outcomes I make in this quadratic polynomial is the biggest question. The linear polynomial is a straight line. The quadratic polynomial is a U-shaped curve, which is called parabola in mathematics. So my first note says that shape of a quadratic polynomial is a parabola, is the important note out here. Now, one more interesting part here is that the shape is exactly symmetric. If I just draw a line exactly in the middle of the graph, then this is symmetric to the other side. This part is symmetric to this part of the graph, is how we understand the geometrical concept of quadratic polynomials. In case of this being a parabola, which is in the shape of, it can be like this or it can be inverted, is how we are going to study in the next session. The parabola can be upward or downward based on some mathematical properties. Now, one of the important property here is also that I get the graph which is U-shaped, but when I see the graph going down, I wanted to know to what depth it forms a crest and then moves up, is also very important. Therefore, in order to obtain this exact point, the point where the graph turns, the turning point can be found by exactly taking the middle value of the both x-intercepts taken. Say for example, to be more precise, I got the x-intercepts as x equal to 2 and x equal to 3. Then I take the middle value of these two x-intercepts, which is 2.5. That implies x is 2.5, or 5 by 2 is the middle value, which exactly lies between 2 and 3. So at this x equal to 5 by 2, I would find the y, and that coordinate will be the point where the parabola turns. So therefore, with this x, I get my y as x squared minus 5x plus 6 is what I get. And therefore, this turns out to be 6.25, 12.5 plus 6. This would be 12.25 minus 12.5, which is negative 0.25. Therefore, I understand that this graph moves exactly 1/4 to the negative part downwards. Minus 1/4 is exactly, if this is minus 1, this turns somewhere here. So roughly, we can approximately find the point where the graph turns, because this is the point where x is 5 by 2, for which I got y as minus 0.25, or this can be written as 2.5, and minus 0.25 is the point where the graph turns. Therefore, this is the point where the parabola turns. Exactly, it turns, takes a U-turn on to the other side, is how we can understand the graphical concept of a quadratic polynomial. The turning point, which we call this as, can also be found by taking the middle value of the x-intercepts and finding the corresponding y. So this, let's recap with x and y-intercepts. Now with this parabola, I clearly see that here the x-intercepts are 2 and 3, because the graph cuts at 2 and 3. So these are the x-intercepts, and clearly the graph cuts y-axis at 6. So this is the y-intercept. These two are the x-intercepts. So always a quadratic polynomial has two zeros, therefore two x-intercepts. Sometimes that x-intercept may converge to form one repeated x-intercept, which we're going to see in the next sessions. Further, the second note I make out here, the third note I make out here is the tendency of the parabola being both upwards and downwards. In case of this, the parabola is upwards because it is moving up, up, up and going into the sky. There are possibilities that the parabola can be even downwards. As we have seen, the shape can be inverted parabola. So when is it upwards and when is it downwards is the biggest question of the note. So here, if I take the parabola in general form, if I take the parabola in the general form, then I say that the parabola is upwards if a is greater than 0. So a greater than 0, this a being greater than 0 implies I get an upward parabola. Straight away an upward parabola. Similarly, when my coefficient of x squared, which is a, is less than 0, then I get an inverted parabola. You can verify by just sketching this on with the table of values. You get an inverted parabola when a is negative. We get an upward parabola when a is positive. So an upward parabola for a greater than 0 and downward parabola when a is less than 0 is how we understand the properties in quadratic polynomials. So now that we have seen the shapes of parabola and the shape of a quadratic polynomial, which is a parabola, and upwards when a is with positive sign and downwards when a is with negative sign. So that is, when a is greater than 0, I get an upward parabola. When a is less than 0, a downward parabola. Now, we have discussed in the previous problem that there were 2 times the parabola was cutting x-axis. But there are some possibilities where the graph or the parabola doesn't cut x-axis or cuts x-axis once, that is, touches x-axis. So let's see the different cases where the parabola cuts x-axis twice, touches the x-axis, and does not pass through x-axis. These are the 3 very important cases which are connected with the 0 of the quadratic polynomial. So let's start with case 1. So when I see this, let me take the 3 different parabolas. Say I take y equals minus 5x plus 6 is this, and then I take another parabola are the 3 different cases which I have taken in case of identifying each of the parabola and its shapes. To start with, I will find the zeros of each of the cases. Now here I clearly identify that the zeros are obtained by taking this equal to 0, and this is indirectly reduced. When factorized using the quadratic formula, I get x minus 2 times x minus 3, which give me the x-intercepts as 2 and 3 in the case 1. When I take this parabola, I get this written in the form x minus 5 whole square, that is x minus 5 into x minus 5 repeated twice. So this is how I get for this. When I use the formula a square minus 2ab plus b square, this reduces to a minus b whole square, that is x minus 5 whole square. Therefore, there are 2 factors, x minus 5 times x minus 5. Similarly, when I take this, I see that I cannot factorize this because the discriminant is less than 0. So to start with the discriminant, I clearly see that here my roots can be obtained by using the formula minus b plus or minus root of b square minus 4ac by 2a, so that I get minus b plus or minus root of b square minus 4ac by 2a, which gives me 4 plus or minus root of this. On further simplification gives me 4 root minus 5 by 2, which gives me an imaginary number. Root of a negative number does not exist in real plane. Therefore, this is understood to be with no real roots. That means zeros of this particular polynomial does not exist. The zeros of this polynomial are 2 and 3. So in case of this, I get a parabola which cuts x-axis twice. So for such parabolas, a is greater than 1, therefore I get a parabola which is cutting twice at x equal to and x equal to 3, where this parabola cuts. Now when I take this, I get a parabola which has been cutting only once, because I get only one root x equal to 5. Therefore, this parabola is said to touch at x equal to 5. So this is how it touches, because it has only one x-intercept which is repeated twice. Therefore, this parabola touches x-axis and then crosses to the other side. Is how I understand the second graph concept. Similarly, when I take this particular graph, the third one, I understand that this parabola do not have real roots, so it does not cross x-axis. So this parabola will be hanging in air but does not cross x-axis to the other side, is how I understand for this. So in each of the cases, I find that when the roots are distinct and real, I have two x-intercepts and the shape would be like this. When the roots are real and equal, I get the parabola touching on x-axis. When there are no real roots, then if it has imaginary or complex roots, then the graph does not cross x-axis and it would be hanging in air. So these are the three different cases which arise through the three different types of roots as we get for a quadratic polynomial. Each of the cases giving different diagrams like this. So note, I conclude here with the first note that roots are, if roots are real and distinct, then I get the case, then the parabola cuts x-axis twice, as we can see the case here. Similarly, if roots are real and equal, in the case of first one being distinct, here if they are real and equal, then the parabola touches x-axis. Here it cuts, here it is touching, because the roots are repeated and real and equal. In the third case, if roots are unreal or imaginary and complex, then the parabola does not cross x-axis or does not cut x-axis. Both mean same. Is how we understand the three different cases as we taken with three different diagrams with example quadratic polynomials. Now let's come with the revision of the session on graphical understanding of quadratic polynomial. So for example, I just draw a graph which is like this. Then how do I understand this graph? I clearly understand that this quadratic polynomial has roots are real and distinct because it cuts the graph twice. So the roots are real and distinct, and because it is inverted parabola, a is less than 0, or the 2 points I understand in this case. The value of a is less than 0 because it's downward is how I test myself with this. Similarly, if I have a parabola which is somewhere here, then in this case I clearly see that if this is x-axis and y-axis and origin, then I see that the graph is not cutting x-axis. Therefore, this has no real roots is the first thing I identify. And secondly, I identify that because it's an upward parabola, a is greater than 0 is how I make the conclusion. Secondly, if I take the third case of so if I have a parabola in this form, then I see that the parabola is touching x-axis. Therefore, I clearly identify that because the parabola touches x-axis, the roots are repeated or real and equal. Therefore, I get the roots are real and equal, and therefore, since it is downward, also I identify that a is less than 0, or the two cases identified in case of this parabola. So depending on the upward and downward trend of the parabola, I can decide the sign of A, and depending on the number of times the graph is cutting x-axis, I can decide the zeros or the roots or x-intercepts of the quadratic polynomial. Is how we understand the graphical concept connected with quadratic polynomial. So on similar grounds of the linear polynomial and the quadratic polynomial, which we have discussed in comparison to the graphical understanding of their shapes, similarly the cubic polynomial with degree equal to 3 is also going to be of similar shape, of different shape in understanding in the graphical part. So what would be the shape of a cubic polynomial when we graph it on a real xy coordinate system is what we're going to see continued with the session. So a cubic polynomial, say for example, I take cubic polynomial in its graphical understanding. So let me take an example cubic polynomial, say p of x equal to x cubed minus 4x. Now that we have discussed about the zeros or the x-intercepts and y-intercepts, I directly draw the table of values before I start with this. Now, as I see this, I clearly understand that I can find my x-intercepts, but I can find my y-intercepts. I can find my x-intercepts first initially by letting y equal to 0, where y is equal to p of x equal to x cubed minus 4x. So when I take y equal to 0, I get x cubed minus 4x equal to 0, so that this gives me x times x squared minus 4 equal to 0. And this further gives me x plus 2 into x minus 2 equal to 0, because this can be raised as 2 squared, where a squared minus b squared is a plus b into a minus b. Therefore, I get 0, 2, and minus 2 as the roots of, or the zeros of the given cubic polynomial, x cubed minus 4x, with degree equal to 3. So as I clearly identify that I have got 3 x-intercepts, makes me understand that because the highest power is 3, which is the degree of the cubic polynomial, will at the most lead to only 3 x-intercepts. If I had the highest power as 7, then at the most I can have only 7 zeros or roots of the given polynomial. So at the most, the roots of the given polynomial can be up to the degree of the polynomial, the value of the degree of the polynomial, but it cannot cross the degree value, as can be seen here with an example problem. Next, coming to the y-intercepts, I find y-intercepts by letting x equal to 0. Therefore, in this case, my y will be 0 cubed minus 4 times of 0, which is 4. So this is my y-intercept, and these are my x-intercepts, is what I obtain separately for x and y-intercepts. Now, once I got the x and y-intercepts, I take the table of values, which I'm going to consider here. This is x and y, 1, 2, 3, 4, and 5. So I get this. Let me randomly take few values on the right and left as 0, 1, 2, 0, 1, 2, and then find the respective y values in case of this. The respective y values out here. So 0, 1, 2 and minus 1, minus 2. So when x is minus 2, I would like to find the value of y, which I obtain by substituting in place of x as minus 2. So therefore, I get this as minus 2 whole cube minus 4 times of minus 2, minus 8 plus 4 to 8, which is 0. As I can also see that when x is minus 2, my y is directly 0. Similarly, when my x is 2, also my y is 0, because this acts as the x-intercept. Also, when x is 0, my y is 0, as I can see in both the cases, x is 0, y is 0, and when x is 0, y is 0. Therefore, this gives me 0, And then when x is minus 1, let's see what the value is obtained as. Which is 3. And then when I substitute x equal to 1, 1 cube minus 4 times of 1 is minus 3, so that I get minus 3 when substituted for 1. So therefore, I get the corresponding points negative 2, 0, this, and this as the points when paired. So let me draw these points on a real xy coordinate system and see what kind of a shape is obtained for this corresponding cubic polynomial. This is x-axis, this is y-axis, this is origin, and then I take 0, 1, 2, 3, 4, 5, 6, etc. And here I get negative 1, negative 2, negative 3, negative 5, etc. And then 1, 2, etc. downwards is how I get the different values scaled on x and y axis. Now let me take the first point minus 2, 0, which I get here as negative 2, 0. So let me plot the first point, which comes negative 2, 0 on x axis is the first point. Similarly, minus 1, 3 lies minus 1 left on x raised on the upwards. Then 0, 0 is origin, which is already plotted out here. Then 1, minus 3 is a point which shifts 1 here and minus 3 out here. This is the point I obtain for 1, minus 3, and then 2, 0 is a point which is obtained here. So I got randomly all the 5 points plotted on the graph. Then I would like to join with a smooth free hand curve, a continuous smooth free using a hand. So then in that case, let's see how the shape would be. It comes here, comes down, touches, goes up, and this is how the cubic polynomial looks in its shape. The cubic polynomial y equals x cubed minus 4x is in the shape of a zigzag crest and a trough, or something like this is how the cubic polynomial looks, which we call in the sense. And now clearly I identify that the graph cuts x-axis at 3 points because I obtained 3 x-intercepts. So minus 2, 0, and 2 are the x-intercepts. And since the graph cuts y-axis at 0, that means the y-intercept is 0, it passes through origin. The specialty of this is that this graph passes through origin, and hence is how I get the shape of a cubic polynomial. So like this, we can construct as many shapes as possible for different types of polynomials. If I have a quartic polynomial, also I would use the similar process of using the table, plotting the points, and then getting the shape. By joining the points, I get the shape of a quartic polynomial. Similarly, when I take a quintic polynomial, a polynomial with degree 5, I similarly take all the 5 points on the table, then I obtain the corresponding y values for the respective x values, then I plot on the xy real coordinate system, then joining the points using a smooth free hand curve, I get a quintic curve. So this is how any curve given in mathematics, we use the approach of finding x and y intercepts and then the table of values, and then I get the graph by plotting the points and joining them by freehand. Is how I understand the polynomials in graphical understanding. So coming to finding, we also know that these coordinates can also be found, as we know that this is minus 1, 3 and this is 1, minus 3, and these are obviously the x-intercepts, and then we get all the coordinates which are plotted here. Now sometimes there are different types of cubic polynomials. Say for example, this is called the standard cubic polynomial or cubic polynomial y equal to x cube. Then what are the zeros of this cubic polynomial? The zeros are nothing but we get 3 repeated zeros as the zeros of this cubic polynomial. So which makes us understand that the graph touches x-axis at 0. So this cubic polynomial, standard cubic polynomial y equal to x cube with zeros as this, will simply have the shape in this form where this touches, cuts, and then goes like this. If I take this as x and y axis, then this is the shape of y equal to x cube. It is something like this. It tries to touch at x-axis and then crosses to the other side, is how we get this standard cubic polynomial. So like that, we can construct using the various different cubic polynomials tested through the table of values, x-intercepts and y-intercepts. Now sometimes I just have the graph given where I need to find the polynomial. Is it possible that if I know the graph, then I can find the equation of the respective polynomial? Is the reverse process of understanding the polynomial through the graphs, where in the previous case we understood the graphs through the given polynomial. So in the reverse process, it is very interesting that I give a graph and we identify the number of zeros and the degree of the polynomial and then find the equation of that polynomial. So let's start with one of the example problem. So identifying the polynomials from their graphs is a very interesting way of learning in the reverse process. So how do we identify the polynomials from the graphs? So for example, I just give the polynomial graph, which I don't know is exactly about its complete description. Then how do I understand this polynomial just by seeing the shape of the graph? Now, as I clearly see, this polynomial has its shape coming as an inverted W, then I see that initially the graph cuts x-axis 4 times. 1, 2, 3, and 4. Therefore, it makes me understand that there are 4 x-intercepts for the graph. 4 x-intercepts or 4 zeros makes me understand that the degree of the polynomial is 4. Therefore, this is a quartic polynomial with degree 4. A quartic polynomial is usually a polynomial with degree being 4, with all 4 roots being distinct, with 4 distinct and real roots, because all the 4 roots are crossing x-axis, therefore they are real roots, is how we understand the quartic polynomial in this case. Let's take another example and see how we can find. So for example, I take now this clearly is an inverted parabola, so I identify that this is a quadratic polynomial and because it doesn't cross x-axis out here, doesn't cross x-axis. Therefore, this has no real rows. A quadratic polynomial with no real roots is how I understand this polynomial just by seeing its graph. Similarly, I have this is assumed to be a straight line with x, one x-intercept and one y-intercept, and because it has only one x-intercept, this is said to be a linear polynomial or a straight line with one real root. So that is how we understand the different shapes through their degree and then define the name of the polynomial: quartic, quadratic, and linear polynomials respectively.